Welcome to Brain Vision.
Okay, so we're doing chapter 26, problem 51. So we have two resistors and two uncharged capacitors shown in this circuit, and a potential difference of 24 volts is applied across the combination as shown. So part A asks, what is the potential at point A with the switch open? It says let V equals 0 at the negative terminal of the source. Okay, so now we can just apply a Kirchhoff loop's law to this small loop right here, and we should see that the equation we get from that is V minus IR1 minus IR2 equals 0. So from this we can solve for what I is, and that's given by V over R1 plus R2. So this is 24 volts over 8.8 plus 4.4 ohms. And that comes to a current of being 1.818 amps. So it says we're looking for the voltage at point A, and it says here is V equals 0. So if we're looking for voltage at A, this is given by the same as the voltage drop across R1, which is given by the current times R1. Sorry, I said R1 here, but this is totally R2, right? So we're looking for the voltage across R2 because we know that there to there is getting to 0. VA to there is 0. So this is R2. So this is I times R2, or 4.4 ohms times 1.818 amps. And that comes out to being 8 volts. Okay, let's move on to part B now. So part B says, what is the potential at point B when the switch is open? So point B. So first we need to know that when the switch is open, these two capacitors are in series to each other. So we know that CEQ is 1 over C1 plus 1 over C2 inverse. If we plug that in, then this becomes 0.2057 microfarads. So this is the equivalent capacitance. So if we're looking for the voltage at point B, since C2 is connected up to the 0 voltage point, this is the same as voltage across C2. We can see, because the 0 point to point B can follow along this track to where it only goes across this one capacitor. So now the voltage across the capacitor is given by the charge on the capacitor over the capacitance. Okay, so let's go back to the equivalent capacitance of our circuit. We can write the equivalent charge of the circuit as the voltage times the equivalent capacitance. We already know the overall voltage drop of across both capacitors is 24 volts. And why is that? That's because we can travel this path, which goes just across both capacitors from the positive 24 volts point to the V equals 0 point. So that means we can take this equation and write this as 24 volts times 0.2057 microfarads. And this comes out to being 4.937 microcoulombs. And the charge stored on the equivalent capacitance is the same as the charge stored on each capacitor. The reason for that is because each capacitor has its own voltage drop such that VC1 plus VC2 equals V. So if you plug that in over here, you'll see why that is going to equal the case. So we can go ahead and write this charge EQ as the same as charge 1 or charge 2. So with that, let's go back to this equation that we had here, and we can start putting stuff in. So if we know the charge is 4.937 microcoulombs, the capacitance is 0.36 microfarads. So we plug that in, and this comes out to being a V voltage at point B of equals 13.7 or roughly 14 volts. Awesome. So let's move on to part C now. So part C says when the switch is closed, what is the final potential of point B? So the switch is closed, and after equilibrium has been reached, there is no current flowing through the capacitors. So the resistors are again in series, and the voltage of a point A must be 8 volts. So again, that just goes to if these capacitors are completely charged, then we can assume that this branch doesn't exist. It's not there. There's no current going through them. So the voltage drop at point A, again, is going to be the voltage across R2, which we already said was 8 volts. So this is still 8 volts. What is the final potential point B? Yes, it is. Oh, so this is point A, but when the switch is closed, VA equals VB because they're connected. Sorry, that was one last step here. So it is still 8 volts though. Okay, so that was all for part C. So let's go on to part D here. I'm going to see if I can fit it in on this page. So part D over here, it asks how much charge flows through the switch S after it's closed. Okay, so we can find the charge on each of the capacitors when they are now no longer in series. There's no current going through them though, but we know that Q1 equals V1 C1. So if the voltage at A and B is 8 volts, that means the voltage drop across C2 is 8 volts. And we already know from this equation we used in part B, that means the voltage across C1 must be 16 volts because the total was 24 volts that we added. So if we use that, we can come back down here to figure out what Q1 and Q2 equal. So this is just 8 volts. Oops, sorry, this is V1. So this is 16 volts times 0.48 microfarad. And this one is 8 volts times 0.36 microfarad. We plug these in and we get a Q1 of 7.68 microcoulombs and a Q2 of 2.88 microcoulombs. Okay, so we know the charge on both of these, but when the switch was open, point B had a net charge of 0 because the charge on the negative plate of C1 had the same magnitude as the charge on the positive plate, C2. That's what we found here, right? So when the switch was closed at C1 equals C2, or Q1 equals Q2. So with the switch closed, these charges are not equal. But the net charge on point B is the sum of the charge on the negative plate of Q1 and the positive plate on Q2. So what that means is Q at point B is now given as negative Q1 plus Q2 when they're closed. So this becomes negative 7.68 plus 2.88 microcoulombs, or it comes out to a negative 4.8 microcoulombs. Awesome. That was it.